Hello and welcome to Critical Thinking Lecture 10. Today we're going to be talking about probability and a square of probability. So first, as usual, we meditate. Assuming you have done that, come back to me. We'll talk about independence. So consider this. Linda's 31, single, outspoken, very bright, majored in philosophy, and as a student she was deeply concerned with issues of discrimination and social justice. Also participated in anti-nuclear demonstrations. Now, which is more probable? Linda's a bank teller, or Linda's a bank teller and is active in the feminist movement. Guess what? It's the first one. Why? Think about the possible ways in which it'd be true that Linda is a bank teller. Here they are. Now compare that with the possible ways in which it'd be true that Linda is a bank teller and active in the feminist movement. Here's where Linda is active in the feminist movement. The intersection is where both of those things happen, right? Now that is smaller. There's a smaller number of ways. So if we're asking which is more probable, we want to look at the larger number of ways. Now this sort of issue, and now don't feel bad by the way, many people get this wrong. It confuses people, I should say, because many people don't assume independence. Now, it's a plausible assumption, especially in this case. An event or situation is independent of another just in case the intersection of the number of ways in which the first and second might occur is the same as the number of ways in which the first might occur and the number of ways in which the second might occur. Here's some things going on in the world, or maybe not involving Linda. Now, we can think of this intersection as before. This is where they overlap. They both happen together. Now, think about this. In a hospital in which 6 male or female assigned babies are born, one after the other over a week, which of the following sequence is more probable? This one or this one? I'll give you a minute. Pause if you like. Neither. We assume, as is plausible, just as before, each of the 6 births is an independent event with an approximately 50% chance of being either a boy or a girl. All right? So, half chance for each of these. The first is independent, as I said before, just in case the intersection is the same number with respect to the ways happening on their own as it is when they're happening together. Now consider, number of ways. This pops up a lot. Intersection as well. This is how you characterize the intersection for independent events. I'm going to show you. You just multiply them together. And the result is that. If you multiply those independent events together, when they are independent, it will let you know the probability of them all, of this sort of setup happening. Now watch this. I'm just going to change the top. This is the other arrangement. Note, it's the same calculation. Now, let me show you why some of this is important. I'm sure you've taken a multiple choice quiz where you're choosing from, say, A, B, or C. You came across a string of answers you believe were correct that fit a surprising pattern, like this, just nothing but B's. I bet you started to think you made an error somewhere down the line. I bet you started to think there's no way your instructor allowed for such a pattern. I bet seeing that pattern made you doubt your previous answers. Patterns like that don't just happen, right? Wrong. If the answers to the test are actually independent, then the patterns like that do just happen. Revising your previous answers because of this pattern may be motivated by fallacious reasoning. We call it the gambler's fallacy. The gambler's fallacy occurs when one infers that because a particular event has occurred more frequently than expected in the past, it will not occur in the future, or vice versa. For example, there's a pattern of BBBB on the test. I'm confident in my answers. It's unlikely there's a pattern of BBBBB with another B, so it's likely the answer to the next question is not B, right? That's fallacious reasoning if we assume that the answers are independent. I can feel it. Now, here's another example. I've lost 17 games of roulette in a row, which is highly unlikely. I should place a larger than normal bet on game 18 since it's even more unlikely that I will lose 18 times in a row. You can probably see the sort of provenance in the name, right? Gambler's fallacy. I can't keep losing. This fallacy emerges because individuals overlook the events in question are independent. Just because you've lost several games doesn't mean you will win at some point soon. Similarly, just because in the past 3 papers in a row received A's doesn't mean you become a soft grader or made a mistake. I'm talking to myself here, of course. Now, I flip a fair coin. Suppose it lands heads 3 times in a row. And suppose it lands heads 7 more times in a row for a total of 10 heads in a row. Now, the probability of that happening is 0.0001. Just before I flip the 11th time, consider whether you think it's more likely that I flip a heads or tails. Remember, I said it was a fair coin. The probability of 11 heads in a row is the same as the probability of 10 heads in a row, then tails. Again, because each flip is independent and there's a 50% chance of heads or tails. I mean, not exclusive. Now, let's use this to build a square of probability. First, of course, meditate. Assuming you have done that, come back to me. We'll talk about probability and possibility. Now, we've dealt with possibility and necessity and logical relationships among them. Remember this. Okay. Necessity is what always has to happen. Possibility is what might. These are boundary cases in the real world. I could get hit by a meteor leaving the house. That's possible. I'm not too concerned about that. I'm more concerned with, say, getting hit by a car or infected by SARS-CoV-2. Each of the proceedings is possible, but some more probable than others. Now, suppose P is probable at the actual world. Remember, P could be any statement, like John is bald. It's probable at the actual world. Do you think that means that it's possible at the actual world? I would say so. Now, suppose P is probable at the actual world. Do you think that means that P is necessary at the actual world? Boo. It seems then we're committed to the following. If P is probable, then P is possible. We can tease out further logical relationships by reflecting on contraposition. Remember what that is? We just take the if-then, we flip it around. Or we take the two things that are related and we flip them around and put negations in front of them. So remember, S is P is synonymous with not P is not S. The contrapositive of if P is probable, then P is possible is if P is impossible, then P is not probable. That seems right. Now, suppose P is true in the actual world. Cool. Does that mean that P is probable? I mean, doesn't it? Right? It happened. Of course it's probable. But wait. If we say if P is actual, then P is probable, we're committed to this. But if we use our contraposition test, then we're also committed to if P is improbable, then P is not actual. Now, I think it'd be worthwhile for you to spend a moment to try to construct a counter example to this before moving on. Just think about it. If something is improbable, does that mean it can't happen? Here's an argument against the claim. Suppose if P is actual, then P is probable. We'll use contraposition. If P is improbable, then P is not actual. This follows from 1. Let's assume something is improbable. Okay. I don't know, black swans or something. According to 2 and 3, that means it's not actual. Okay. But sometimes improbable things do happen, as a matter of fact, in the actual world, which contradicts line 4. So that means we can't accept 1. We've got ourselves a contradiction. We use reductio reasoning, so it's not the case that if P is actual, then P is probable. Now, let's use this reasoning to embed into the modal square. Here we go. Built this thing for us. Let's talk it through. Over here in the upper corner, we have probability of P equaling 1. Remember, up in this corner we had things like all S is P in the traditional square. We also had necessarily, so it had to happen in all possible worlds. Here, it's very similar, right? When we say probability of P equals 1, we mean 100% of the chance, right? Or 100% of the times it happens. So, on the other hand, we have over in the right corner, we have probability of P being 0. It means it never happens. It's impossible. And necessary and impossible line up on the tops of the corners of this square, just as they do with the modal square. There are, of course, contraries. You can think about that. Go back and look at your notes. Think about what a contrary is. Now, of course, probability of P being 1, the contradictory of that is going to be what? Look across. Probability of P not being 1. Similarly, the probability of p equaling 0, contradictory there. Probability of p not equaling 0. Remember, these just flip the values. They just put a not in front of them. Now, this is all to say that probability of something like p equaling 1 nevertheless entails all the way down to probability of p not equaling 0. And that should make sense. So the probability of p equaling 1, for instance, entails that the probability of p is greater than or 0.9. Similarly, that also entails that the probability of p is greater than 0.6. And all the way down to probability of p not equaling 0. So now on the other side, we have probability of p equaling 0 entails that the probability of p is less than or less than 0.1. All the way down to probability of p being less than 0.9 and probability of p not equaling 1.